going to get quite technical. Probably the most technical thing that we're going to talk about today, because we're starting to talk about the core primitive of the protocol, and I'll explain why it's so central. And so this is the thing I've been teasing all day. The other thing is with the sort of crypto condition standard, that's the first spec that we want to work on. That is the spec that everyone has to support if they want to be ILP enabled. All the other things, we can sort of build adapters, we can work around differences, but that's the thing that everyone has to agree on. So that's why we're emphasizing it so much. Okay, so this is kind of from the presentation earlier today. We talked about this receipt that the recipient is generating, and he's passing it on, and it goes to the ledger, and then it goes to the connector, and it goes to the other connector, but we haven't really explained what it actually is, what's actually in this receipt. And thank you, Bill Nye, for pointing that out. And thank you for doing it in a public domain image rather than so the main thing about the receipt is basically it's what allows the ledger to make that decision between either rolling back the transaction or executing the transaction. So we said that escrow is really crucial in the protocol, and that means that the escrow has to be resolved at some point. We have to either decide that the transaction is not going to happen, and so we want to roll back, or we have to decide that the transaction does happen, and so we want to execute it forward. And every ledger has to make that decision at some point. The rollback in Universal is pretty straightforward. It's just a timeout. It's like if nothing good happens for a while, eventually we give up and we just roll back. What's a little bit harder to conceptualize is what success actually looks like. Like, what does it mean for a payment to be successful? How do we define that in a way that's deterministic? And so, well, the person who's initiating the payment is the sender, and so as a sender, I want to be certain that what? I want to be certain that my donation has been received. If I'm donating money to a charity, I want to make sure that they got it. If I'm paying an invoice, I want to make sure that that invoice is now paid and settled, and I don't have to worry about it anymore. If I'm paying up for a loan, like I want to make sure that that is settled. And ultimately, those all generalize to I want non-repudiable proof of settlement. And so the proof of settlement part is the money got there, and the only way to know that is that it got there all the way is to get proof from the recipient. And I want it to be non-repudiable because I don't want the recipient to later go, no, actually I changed my mind, you didn't pay me, and so now I have this awkward situation where, no, actually you gave me this thing, so I want to make sure that this is proof that they can't renege on. So just to summarize, you have this receipt. It has to be something that's signed by the recipient. It's something that proves receipt of funds. In Interledger, we have a little bit of this quirk where the recipient produces the receipt before the money goes into their account. But the way that we think about that is they warrant that the money has arrived on their ledger, the ledger that they're using. It's arrived in the currency that they're expecting. It's the right amount and everything. And so signing the receipt and actually receiving it into their account is considered to be one step. It's considered to be part of the two sides of the same medal, if you will, because the recipient and their ledger are very closely coupled. They're two collaborating parties. We want to make sure that it proves the receipt of funds, as I mentioned. We want to make sure it's non-repudiable. It could have some data attached, but again, we're very cognizant of like the different protocol layers, so we don't necessarily want to specify what the data has to look like. Although that's definitely it's more of an open question in terms of like, what is that data and what does it look? What could it look like? And it has to be pre-agreed on before the payment. So before we even like put any money in escrow, the sender and the recipient have to agree what success looks like. It's generally good practice for any project to first agree what success looks like before you engage in the project. But here it's really, really crucial because you don't want any ambiguity afterwards. You don't want any case where some parties say like I did my job and then other parties like no you didn't. Like you have to be very clear what success actually looks like. And so I mentioned that the receipt has to be pre-agreed. Okay, so what that means is that we can't give the ledger the receipt when we're setting up the payment, right? But we have to give them something that kind of describes what it's going to look like. We have to give them something which is like, you're going to get a message, you're going to get a signed message that looks kind of like this. And so we have to figure out what these two components are, the description up front and then the actual format for the message afterwards. So when they get the receipt, then they should be able to match it and then decide that it's okay to execute the transfer. And we call this description, we call it a condition. So a condition is basically a piece of data which is a description of a signed message. Okay, so I give you this condition, and then any signed messages that you get, you can kind of compare, see if it fits, and if it fits, it's a fulfillment of that condition. Okay? And so that gives us some language, and it gives us some tools to express how these escrow conditions are executed, because we can say, well, the escrow condition is this, and if you get that fulfillment for that condition, then you should execute it. And if you don't get the fulfillment before the timeout, you should roll with that. Okay. Now, here's this really crucial point of like, why are these conditions so important? Well, if you have one ledger that is receives the execution, the fulfillment, the receipt, and they execute the transaction, and then the connector tries to pass that receipt to the next ledger, and that ledger disagrees, they don't think that this is a valid fulfillment, then the connector loses money. And not in the way that we're talking about, like, oh, the connector has to take some risk, or oh, the connector has to make sure they get the message through in time, but this is a way which you can actually force on them, right? You can actually generate a receipt that you know is only going to be accepted by one of the ledgers, so you can deliberately screw the connector. So this is very, very bad. And we have to absolutely prevent this from ever happening. And what that means is that the conditions have to be bit perfectly enforced by the ledger. Now, that doesn't mean that the ledgers have to support all of the same types of conditions. So there could be some differences. Some ledgers could have more features than others. But they have to know upfront, if you have two ledgers, you have to be able to know for sure that the fulfillment is going to be supported by both of them, and that the particular fulfillment that you're waiting for is going to be accepted either by neither of them or by both of them. So we need to come up with some scheme that has all these properties that I mentioned, and that's what I'm going to talk about now. So first, the good news. Okay, this sounds really complicated, this sounds really hard, but others have actually done the really hard work for us, which is cryptographic primitives that you need to build this on top of, signatures, hashes, are already defined. So we can like kind of look through the library of standards around cryptography and pick some of those out. We don't have to reinvent the wheel there. And really, like, these standards are a bit perfect because that's exactly what a signature needs to be also. It's like it needs to be very clear. If you get a signature, is it valid or not? And everyone has to agree on that. So these standards are very precise. Sometimes not as precise as you'd like, but pretty close. And so I consider the hard part really done. So you just have to build something on top of this work that already exists. So how much do we have to build on top? Well, are simple signatures enough? Can we just say, well, the recipient signs it with RSA, with ECDSA, and then we're done? So that would look like this. So we have a signature condition, which is basically you have this condition, and there's some public key that you're expecting a message to be signed. You might specify the message, you might specify part of the message, but essentially you're associating this key with this condition, and you're done. Well, there's something that might immediately stick out to anyone familiar with cryptography, which is like management of keys like that is really hard. It's very easy for a system to get compromised, and then that key is floating around. And so one way that people address it is by having sort of multiple keys. So we can extend this a little bit and say, okay, maybe we define multiple keys, and then if a certain threshold of them have signed a message, then that's good. And then that kind of makes our system usable even in very high security contexts. And so again, the question is like, are we done now? Is this the only thing that we need? And so at this point, I want to kind of look at some of the other things out there. A lot of people are working on very similar problems. So one thing that sticks out immediately is Bitcoin scripts. So Bitcoin scripts are essentially trying to solve a similar problem where you have these signatures, and they want to add a little bit more expressiveness around that. So they want to kind of support more use cases. And so there are a little bit of opcodes added other than just hash this or verify the signature. There are things like, concatenate these two strings or compare which of these two strings is bigger, etc. Now, a lot of those opcodes have been disabled in Bitcoin early on, and they still haven't been re-enabled. People are working on defining them precisely enough that the people would feel comfortable enabling them. And I'll go into some of the challenges with that later. But one thing that I'm noticing, and this is from working with Bitcoin for 6 years and kind of looking at a lot of the use cases of Bitcoin scripts, the thing I'm noticing is that a lot of the use cases essentially boil down to some form of multisig. I pretty much picked this example at random from one of the use case pages in the Bitcoin wiki, and it happens to be one that uses multisig. But really, that's not as unlikely as you might think. A lot of the use cases boil down to some form of multisig. And that's going to become important in a moment. There's a lot of other efforts out there. Jehan talked about state channels right here at the bottom. There are pay-to-script hash tree signatures. Tree signatures are ways to express multisig more concisely. Merkleized abstract syntax trees is something that's fairly close to what I'm about to talk about. It's basically having these opcodes be hashed individually and then structured in more of a tree shape. But one thing that all of these have in common is they kind of fall in this spectrum between you have the pure simple signature, single signature system, or maybe multi-sig system, and then like this full Turing complete programming environment. You know, like Ethereum has like a deterministic programming language that lets you express like any kind of cryptography you want because it's Turing complete, and it has like a lot of flexibility. And the thing that's holding us back from adopting the Turing complete option is you have to remember it has to be bit perfect. So everyone who executes this contract has to execute it in exactly the same way. And we don't have the luxury that maybe a blockchain would have, where it's okay to have one implementation and everyone uses that implementation. If there's a bug, well, everyone has the same bug, and so it still executes in the same way. So we don't get that decorrelation. But we are trying to build something that people can very easily implement in different languages, and so it becomes a lot harder to have this like one language that everyone in every language is perfectly implementing down to the last bit of how the language behaves in every case, in every possible scenario. Another person that I don't know if they're okay with me quoting them, so I won't mention the name, but they kind of call this the ActiveX of blockchain. It's kind of like programmability has been a bad idea. Well, not a bad idea, but like certainly the point of entry of a lot of security exploits. ActiveX especially has been famous for that, breaking Internet Explorer security over and over and over. I don't even know if you can call it breaking the security because it had very little to begin with. But there's other examples like Flash routinely gets exploited because of its rich feature set, and people use Java for exploits again because it's a programming language. So programming languages have notoriously large attack surface. And so the question is there something that's kind of a little bit more middle of the road that gives us most of the benefits of a full Turing complete language and still isn't all that complex, something that we can standardize quickly, V1, get started, and again, serve a lot of use cases still. And kind of a little bit of a throwback and a little bit of a sidebar here on an idea that's been around in Bitcoin for a long time that we kind of picked up with Codius, which is the idea of a smart oracle. So you kind of remember that the first slide I showed where you have a key and then that key is associated with a condition. Well, a smart oracle is basically something that lets you associate some code with a key, okay? So rather than teaching or making a condition that can contain code, you just have a key that represents someone else running that code. And it's kind of like, it's a delegation or a deferral. And you can do that with one host, or you can do that with multiple hosts. And what you notice is someone who wants to validate that condition now only needs to be able to validate those signatures. They don't need to understand that code. So it's a kind of a nice little principle that you can use to encapsulate very complex relationships, very complex business rules, just as signatures. And it's just a very simple concept to do that. Okay, so I talked about delegation. And delegation is basically the generalization of that. So if I can say that if this guy tells you yes, that means you should execute. Or if these two people say yes, then you should execute. So it can kind of express like, who am I delegating to? Then in terms of who actually knows the rules that you should be enforcing. Okay, and I could do the M of N, and that gives you a lot of flexibility. And again, like I don't know what Bob, Chandra, Lena are doing. They could be running really complex code. They could be querying external systems. They could be doing all sorts of things. And one point I want to make is on the security model. And again, this is going to take a minute, but I think it's a really important point, which is a lot of people kind of look at this and say, well, but you're losing security. And the idea is kind of like you have your blockchain that's enforcing your condition, and that's your security level right here. And then you have this external system, and that might have a security level that's higher or a security level that's lower, but you're adding a dependency on an additional system that you now also have to trust. And I look at it a little bit differently because remember this active X effect, right? So the fact that this blockchain, the alternative is having the blockchain run all the code. And I think that that kind of creates like an inherent limit of like what kind of security level you can achieve if you have this really complex blockchain implementation that maybe there's only one implementation that's actually fully complete. And so it kind of puts a ceiling on how high your security level is to begin with. Whereas like if you have a blockchain that just enforces this delegation rules, that can be very simple, so they can have a very high security ceiling, so very secure. And then you can have a system that runs very complex smart contracts, and then you can have one transaction that refers to this system, and it has all that expressive power that we got from option A. But then you can have someone else who's using the same blockchain that has a very high security ceiling, and they're using a much simpler smart contract system. And so that has a smaller attack surface. And so I can actually, I think, overall increase the level of security by using this method. That's as much as I'm going to say about that. If you, like, I'm sure many people will disagree with that, so I'm happy to debate that. But that's as much as I have time for right now. Okay. There's one problem with this view, which is there are some examples of delegation that we can't yet express. So for example, here, we want to make sure that Bob always gets asked. Bob has to say yes. And then there's these two other systems there, maybe there for redundancy or something, where we only need one of them to say yes. And that's a case that we can't just express with M of n because, it's kind of like, if Chandra and Lena say yes, then there would be 2 out of 3, but that's not a case that we want to support, so we have to kind of come up with something a little bit more flexible. And so this is a case for Boolean circuits. So we have these inputs where people are saying yes to a transaction, and we're kind of trying to create the structure, describe the structure under which we want to arrive at an overall yes. Okay, so we have Chandra and Lena, that one of them has to say yes, and then that has to be fulfilled, and then if Bob also says yes, then we can say yes overall. And so these are the basic primitives of Boolean circuits. It's nice to introduce sort of the M of n concept, because it's like sometimes you want and, which is kind of like n of n, and sometimes you want just or, which is 1 of n. So we can kind of use M of n as a thing in the middle if you really want to express thresholds. And then, of course, we notice that, well, and or are just special cases of that. So if we have an M of n Boolean threshold gate operator, then we can express all of these different types of relationships and trees. So if we take all of these different concepts and we kind of put them together, this is what we end up with. So we had the concept at the beginning of we have a condition which is just basically a signature condition. So if someone signs something, then the condition is fulfilled. And we have this M of n concept. And we said that rather than making just an M of n of signatures, which would be too limiting, we can make it an M of n of conditions. And so we can stack these any way that we want. The leaves are always signatures, and then the thresholds are always of other conditions. Okay. So let's talk about the fulfillment and get into some practical examples. So again, kind of going back to the original problem statement, we want to have a description of a later signed message. And so here's an example of a signature condition. The condition consists of the bit mask. This is actually from the spec. The bit mask, which is basically the type of condition that you have, it consists of a hash, and then the maximum length that you have to be able to handle that the fulfillment could have. And that's kind of to get that determinism. So if you imagine there are 2 ledgers, and one accepts very large fulfillments and one doesn't, it's important to know that beforehand, because otherwise you can again get into a situation where one ledger accepted your fulfillment and one didn't, and so now you've lost money. And that's so in a way where people can actually force that to happen. So you have to know what the maximum fulfillment length will be, so that either both ledgers reject it because the fulfillment is over the length, or both ledgers accept it because they've both already checked the length because they've seen it as part of the condition. Okay. This hash part in the middle, here's the description of how you generate that hash. So in this case, it's for an RSA signature. So first we put like a type field again, this time with a full URI. This is kind of to make sure that there's no ambiguity. And then it has the public modulus. It doesn't include the exponent because we just defined in the standard that everyone should use the same exponent as the 65, 37, yeah. And then the message prefix, which is part of the message. I don't want to get into like all the details here. There's some neat things going on. And this is what it actually looks like. So this is from the reference implementation or the test implementation I have. This is what a condition actually looks like. And it's basically a little prefix, and then it's the base 64 encoding of this condition object that I showed you. Okay. All right, so now how do we fulfill this with an actual signed message? Well, we need, again, the type. We need, again, the modulus and the prefix. So this is basically to make sure that the fulfillment actually contains all of the information that we need to generate that hash, so that we can actually verify that this is a fulfillment for this specific condition that we've presented previously. And then it has the actual full message that is being signed, the signature itself, and then this last field, which is bytes unused, which is basically needed to, if I give you this, you need to be able to calculate what the maximum fulfillment length would have been. So you need a field that kind of tells you how many bytes you didn't use out of the maximum, so that I can take the actual length, add the unused bytes, and calculate the maximum that it would have been. So this is what that looks like. So again, you have this sort of prefix, and then you have this base 64 encoded set of values. Okay.
We just have the hash name and revelation as a condition.
Yeah, so right now I'm using signature conditions using RSA as an example. The reason you'd want to use that over hashes is because you can generate that offline. So if I have some scheme that's building on top of ILP, that is, and I need to know what the recipient's condition is going to be. If I use asymmetric signatures, I can generate that myself because I know their public key, and I can have some deterministic way to generate the message. So I can generate that offline without having to do a round trip. Whereas with hashes, I always have to go and ask the recipient what the hash is for each individual transaction. So it's just an optimization that you can use for certain use cases. In our case, what we do is we actually have, like, I'm a little bit dishonest here because I'm showing two types of condition. In the actual implementation, there are three types where there are two signature types. There's the hash-based one, and then the asymmetric one, right? But I'm using one example here because they're very similar. They're just like in one case you get a public key and a message, in the other case you just get the hash and then the preimage is the signature. So you can almost think of the hashing function as like a different kind of signature algorithm. Okay. Here for the threshold condition, you get the exact same format for the condition. So again, you have the type field, you have the hash of the condition, and you get the maximum fulfillment length. And the hash is calculated a little differently. So the hash is calculated by the threshold of inputs that are required to fulfill the condition, the total number of elements, and then for each element you take the condition. So not the fulfillment, but the condition in order to generate this hash. So let me just go ahead. And so what you notice is that the condition looks exactly the same. And so one thing that we noticed with the reference implementation is that with our previous format, which was more JSON-based, there were a couple things that were issues. So one, it tended to make the overall transfer objects very verbose because you had to include the entire description of the condition every single time. And it also is a little bit harder to index something by condition. So if, let's say you have an endpoint where you accept these fulfillments, and the fulfillments can be delivered using any transport, they can be delivered any way by anyone, it can be completely anonymous to submit fulfillments. And you need to know if this is actually a condition that you're expecting a fulfillment of, right? And so it's very easy to have that sort of index if the condition is in a nice like string-based format, as opposed to a more broken out JSON format. Another reason for this kind of format is that we actually want to discourage people from modifying the conditions. So like the way that you should deal with the conditions is everyone should generate them deterministically based on the scheme that they're using. You shouldn't like let someone else generate it and then try to verify it, because what tends to happen is that they will put something in there that you don't understand. You forget to check for that thing because you're just parsing whatever they gave you. And so now you have a condition that might contain something that actually breaks the security for you. Whereas with these sort of opaque strings, if both parties generate it, it's very easy to compare that they're the same because you just do a string comparison and now you know that they're the same. Okay. So here's the format for the fulfillment for the threshold. And it's the type. So we need all the fields again that we used for the hash. And then we have the actual elements, which are this params field, which is basically whether it's fulfilled or not. And then you have either the condition or the fulfillment, depending on whether you're actually trying to fulfill that branch. Here's the actual example. And one thing you might notice is, okay, this is a 1 out of 2 threshold condition fulfillment, and it's barely longer than the signature fulfillment example I showed you earlier. And you might be asking, like, why is that the case? And the reason for that is because we're only giving the full information, like the public modulus and all that data, for the subconditions that are actually being fulfilled. Okay, so we're not giving all the information for the subconditions that are being ignored. And that's kind of similar to this idea of Merkle abstract syntax trees, where it's like you're only actually giving the full condition for the parts that you're fulfilling, which is sort of this concept here. So you have the full receipt or the full signature for one of the branches, and the other one is still just the condition, just the hash. And that could represent a much more complicated condition with many, many, many subconditions. But all you're providing is the hash of it, because you're not even claiming that you're fulfilling all of that. It's a dead branch, it's a falsy branch, so you just give the hash and move on. Okay. So that's all you have to submit. So just to recap, there's 2 condition types in the current spec, the signatures and the thresholds. The conditions are constant size, so it's very easy to work with. So if you wanted, for example, to take, let's say a recipient wants to get paid, but they want to get paid in order to pay someone else, what they can do is they can get the receipt from the payment that's happening further down the line, take that receipt and make it a subcondition in a different receipt, where like maybe they're using AND to take that receipt and then their own signature, and then they pass that on as the receipt. So you can kind of abstract away a very complex condition that you don't care about, and you can just deal with these very short, constant size descriptions of conditions. During execution, falsy branches can be omitted. That can be very, very useful if you have things like an offline override option. So if you have a condition where one branch is, this is the CEOs of the company coming together to override the system, and there's a lot of keys in there, and the keys are very large, and we don't usually need that ever, because normally the system operates normally, and we just don't use that whole part of the tree. And so we can replace that with just a hash and not even give it every time, right? So you can have pieces of your conditions that are very complex and yet never show up in the protocol during normal operation. And the only time they would show up is when you're actually trying to use that branch for something to prove something. Any kind of complex logic is intentionally left out of the scheme. So again, we could have made this into a programming language. We could have turned it into, you can concatenate things and add things and divide things. And we think that it's much nicer to have a simple description of delegation, and then have whatever business rule systems that you want to have that are actually enforcing these more complex relationships somewhere else, and then present a signature that you can describe using the scheme. Some other features that I didn't get into as much is the conditions can be generated from the fulfillment. So that's, again, in order to look up which condition is actually being fulfilled, you can just if I give you the fulfillment, you can generate the condition. So that's a general property we want for all of the conditions is, again, if you get the fulfillment, you can generate the condition, you can do a lookup, whatever you want to do. The maximum fulfillment length is stated in the condition. Again, it's important, as I mentioned. The whole thing is extensible to new primitives. So right now, the example implementation that I've built that has like an RSA condition, a SHA-256 condition, and a threshold SHA-256 condition. So 2 of them are basically representative of the signature condition. 1 of them is representative of the threshold condition. But these bit fields that I'm using for the types are extensible so that people can define other algorithms in the future in order to extend that with new algorithms.
So if I want to use a different crypto primitive, there would be like a byte in the serialized format that I would switch from 2 to 8 or something. It would mean that it was.
Yeah. So. Exactly. So we actually, there's a couple things to that I might want to show off a little bit. So this is under 5 belts condition. Private. Okay. So here's some example code. Again, this is like super early. This is just 1 weekend's worth of hacking this together. Basically, here are some of the things that you can do. So if I give you a condition, you can validate that it's valid. This would check things like based on the bit mask in that condition, do I support all of the features that this condition claims that it needs? So again, this is this first field that I showed before the hash. And that's where the typing happens. So right now we've defined like 3 bits, which is like 1, 2, and 4. And those basically represent the SHA condition, the RSA condition, and the threshold condition. And the reason they're separate bits is because the threshold condition can, of course, you don't know what it contains. It could contain either of the other 2, right? So you can have a threshold condition with only hashes in there, right? So but that would be 5, right? Because the bit 4 and the bit 1. And so, or you could have a threshold condition that has both types of condition in there. There would be a 7, right? Because it's 4 plus 2 plus 1. And so we can look at just this bit mask and see if the set of bits that we support, like the set of algorithms we support, has all of those bits. And if it does, then we know that this condition is the condition that we can actually execute. If there's any algorithms that we don't support, like for example Bitcoin, there's no way to express the RSA condition because Bitcoin has no RSA. And so because of that, Bitcoin would not have that bit set. And so if 2 connectors are trying to make a transaction through Bitcoin, they would not accept any transaction that has a condition that has any other bit set other than the basic hash lock SHA-256 bit, right? Because they can't be sure that the ledger will actually enforce that. And then similarly with the maximum length, Bitcoin has certain limits on how long the scripts can be. And so if you have a preimage that's longer than that, you could potentially trick a connector and kind of submit a condition that one ledger accepts and the Bitcoin doesn't accept because it's too long. But the connector can check the maximum fulfillment length to make sure that the fulfillment is going to be below that length. And if it isn't, then both ledgers are going to reject it, even the ledger that would support larger fulfillments normally. Okay. I think I'll take some more questions from here. Here, Aaron.
Is everyone kind of comfortable with where
Could you implement this without any further kidding?
I'm comfortable with the fact that Stefan's been head down working on this for a very long time.
Yeah.
And he's just done about 6 months of really hard work.
See, if you had said yes, you'd be hired now.
In 30 minutes. So I mean, is everyone comfortable with where this fits into ILP? I mean, in terms of the fact that,
yeah, so maybe I can spend a little bit more time just context studying. So first of all, one thing I'm noticing is that this is very nicely orthogonal to what Johan's been talking about because everything that I've said is still about deciding on one bit of state. So we're not dealing with the content that's being proven by the condition at all. Whereas Johan, all he's talking about is the content of the condition and like the state that's being agreed on, and the thing that's fixed in his model is the signers, right? You have 2 signers always. And so it seems like the 2 things would nicely combine where like we bring the flexibility in terms of what the signers are and state channels, and your work brings the flexibility in terms of what they're actually agreeing on. Rather than just one bit, it could be more involved in that. And that's one sort of starting point and like area of investigation that we want to pursue.